Talk is starting, sorry. Talk is starting. Okay. Great. So our next speaker is Maryam Dehnavi. I'm not sure how to pronounce the first. Stoic or
Stoic.
Stoic. Okay. And Patch, a co-design approach for unstructured sparsity in AI.
Thank you. Thanks for coming to the talk. Before I start, I wanted to thank all my students. Victor and Arya have helped significantly on building Stoic, which is a sparse compiler, and Mohammed and Yunus have helped with building Patch, which is the co-design part, where you build recipes, ML recipes for unstructured sparsity. So as models get larger, and if hopefully we eventually get convinced that environment matters, we want to make inference go faster. And so compression is becoming more and more important. Quantization is one approach to compressing our models, which you reduce the precision of the numbers by rounding them to the closest integer. And it's actually mainstream right now. For sparsity is where we set the non-important weights to zeros. And for the context of this talk, I'm going to talk about 2-4 sparsity, which is a form of structured sparsity, where out of 4 consecutive elements in your matrix, at most 2 are non-zeros. Now, why do I kind of separate these into a class? Because there are sparse tensor cores that support their execution. And then the other class are unstructured sparsity, where the non-zeros can hypothetically exist anywhere in your matrix. But there is no hardware support for these. Now, in this slide, I'm going to show kind of why quantization has hit a wall, and we need to go and take sparsity seriously when it comes to model inference. So here I'm showing you Llama 2, 7 billion parameter model on 8 zero-shot tasks. And we're trying to compress the model. We want to go out to 8 times compression. The accuracy of the dense model is 54-something%. With 4-bit quantization, that's actually quite easy to accelerate. You get 53% and something in accuracy, which is really good. So you get very little loss in the accuracy and quality of your model. But if you go further, there's a huge drop in the accuracy of the model. Yes?
The base was 16-bit?
Yes. Yeah. And so the solution is to go and use sparsity. 2-4 sparsity is the low-hanging fruit, because NVIDIA, it's been a couple of years that the 2-4 sparse tensor cores exist. And you actually get quite a bit of that accuracy back. But the gap is still not acceptable by practitioners. This is still a big enough gap for them not to adopt 2-4 sparsity.
What's that accuracy of?
It's the accuracy of the model during inference on the test that you run. And so the solution is to look at unstructured sparsity, where, as I noted, because of the freedom you have on the location of non-zeros, you can decide not to zero out your important weight values. And this gives you the compression you need and actually regains a lot of that accuracy back. So why isn't unstructured sparsity adopted? While it preserves model quality, there is no hardware support to accelerate these. Yes?
In your previous slide, when you say unstructured sparsity, is it also like 50% or?
This is 50%. When you do, we do 50% unstructured sparsity, yes. But I'll talk about Patch, and you have the knob now. We can provide the knob through Patch. Like, you don't have to get stuck with 50%. So now there are software solutions to this. We've done work on that, where we build code generators and these solutions that specialize code for the given sparsities. The problem is the kinds of specializations you could do often don't work well on GPUs. And when they work, they don't work for the sparsities that the AI models work for. And this has created a disconnect between the people that build systems and code generators. Yeah, we have a question. Oh, whoa, what happened? I will accept whatever you want me to accept. Let's go away. OK, so now this has created a disconnect. So the model builders and the people that build AI recipes, when they tell them unstructured sparsity, they think, OK, I have the freedom to place my non-zeros anywhere. And then they build these high-quality models, and they go back to these backends that are actually extremely hard to use. And even for like our own work, and we wanted to compare to current code generators for unstructured sparsity, it took an eternity to even install and make them run and be stable. Not only that they don't support the kinds of sparsities the practitioners want them to support. So this is why we introduced a new form of unstructured sparsity, which we call a tile-based unstructured sparsity. So this is kind of meeting everybody in the middle ground. The people that are building these systems for AI are embracing tile-based programming models more and more these days. For example, if you're aware of OpenAI Triton, if you're aware of NVIDIA Tile IR, and many other models that exist out there these days, they expose the tile programming model to the AI practitioners. Actually, yesterday I was at Triton Dev Conference, and PyTorch now has a new API that you can explicitly talk about tiles. So that's how comfortable they've made these practitioners be with tiles. And on the other side, when it comes to accelerating anything on a GPU at least, tiles are really good fits because you want to tile things, you want to reuse them, and you want to be able to express your schedules around that. So we decided to build a model recipe and a compiler, which we call Stoic, for tile-based unstructured sparsity. What do we mean by that? So we first tile the matrix, and now we allow these tiles to be dense or sparse anywhere. That's where you have a degree of freedom. And then when it comes to the sparse tiles themselves, we allow you to decide where those non-zeros are, as far as you make sure they are true for sparse. So let's talk about patch, because you can always build a system. And if there's no model to run that system, you can't prove a case, and this will go again into the archive of everything else you build. So what we do with patch is we take a model, and instead of making each layer separately sparse, we aim for an overall model sparsity. And as a result of that, some weights that are more important become kind of less sparse, and the weights that are less important become more sparse. So the post-train approach that we take here takes the entire model into account and eventually leads to these weight matrices at each layer that are tile-based sparse. How do we do that? So you saw that matrix. You actually had, you saw this matrix. It has 9 tiles. So we assign a parameter to each tile. We use Gumbel softmax because we want to assign them continuous probabilities so they're differentiable. And Gumbel the softmax also allows you to introduce noise into these probabilities. And then the higher the probability goes during your post-training approach, you're going to kind of over 50.5, you're going to make that tile dense. Below, you're going to make it sparse. So that's one thing we do. Then for all the tiles that are 2, 4, when you have 4 consecutive elements and you have the option of making 2 of them non-zeros, you have 6 options. So you give a probability to each of these options that you have, and use, again, Gumbel softmax. And now you jointly post-train your model to find out the best mask to get to the accuracy that you need with the goal of the sparsity that you kind of put for your model. So we have 2 additional terms right now that we introduce. One is the sparsity regularizer. What it does is it makes sure that you get close to the goal end sparsity of the model that you wanted it to be. And if you're familiar with diminishing gradients, what happens during this process of post-training is that the weight values start going down. You want to stop them from going down. So you introduce that as you introduce a regularizer to the loss as well. With all that, we end up with a mask that then we clip it. Wherever is kind of green here will become a non-zero tile or a non-zero element, because this is considering the 2-4s as well. And then we multiply that by the weight. We now have pruned weights for each layer. And not only that, you have a tuning knob. You're able to decide how much sparse you want your model to get, because you're trading off accuracy for speed. So here the percentage is actually the sparsity ratio. We are not going above 50% sparsity. We want to find, for now, a good kind of control between all dense and something that is all 2-4 sparse. And as you see, the accuracy actually is really, it becomes really good. And what I've shown on the side here is if you add an additional LoRa to your model, then you can even gain more of that accuracy. Yes?
How come the accuracy increased when sparsity decreased?
Oh no, this is so the sparser the model gets, the less accurate it gets. This is like 25% sparsity is less sparse than 45% sparsity.
What was less?
The sparser you get, yeah.
What are the red percentages on the edges of the?
Yeah, so good point. So this is the amount of accuracy you gain compared to this. But this is the difference. And this is adding slim LoRa that I'm not going to talk about in this talk. So you can add another level of low rank updates. It comes with a cost. We measure that cost. I'm not going to talk about it here. But that allows you to regain that. And that can happen during the same post-training. Yeah.
So 2-4 sparsity is 50% sparse.
Yes. If you go anything below, you don't gain anything. Because 2-4 sparsity really means you have the freedom to at most make 2 of the elements non-zero. But you want to be at the at most, because your speed up's not going to change, and you're going to lose accuracy if you go anything below that.
So you are actually less sparse than 2-4 sparsity.
Yes, we are.
You are more accurate.
Yes. It's exactly a trade-off. It's a knob. That's it. And if in future, which I'll talk about, this is not very easy to do, but if in future we add lowerings for a CSR tile that's efficient on a GPU, then we can continue playing with this. But for now, this is, yeah.
How does this compare to the actual runtime, like training time and inference time?
I'm going to talk about it. It's after I talk how to accelerate this, because I gave you no guarantees up to now. Yeah.
Does there's no reordering of, okay.
I mean, you can, but we don't do it. We don't have to do it here. Actually, if you take it's an extra step and there's no guarantee. You can always reorder things. You can take a weight matrix, reorder it, and then see if you can further specialize. But that's what we're running away from. We want to reduce we have work that we've done that. It's usually not successful for these kinds of sparsities, and it breaks the co-design idea. You want this knob to exist, and you don't want to start overplaying with your sparsity. But yeah, I mean, it doesn't work as well. And you can always reorder, and then now you have a bunch of your tiles that kind of your dense tiles might sit at maybe aligned columns. But then if you have a good schedule that I will talk about later for that specific alignment, then be it, you can do that too. It doesn't break the kind of tile base. Yeah.
How big are these tiles, like when you're partitioning the matrix?
It's a very good question. So we decide what these tiles are from Stoic, from the backend. So the backend is a feedback loop. Okay, for this accelerator backend, for this type of GPU, we need tiles. We can tune further down, but you better post-train your model for a 128 by 128 tile. Specifically, these patch results are out of a 128 by 128 tile. Okay. So now let's talk about Stoic, because another aspect of this is tile-based programming models are really cool. They're easy. People want to express their schedules through it. So why don't we have any compiler to support it? Actually, OpenAI Triton does not support sparse tiles. So what we did is we took Triton and we added sparsity, tile-based sparsity to it. So what happens here is there's an inspection phase. Like everything, we always talk inspectors and executors and sparsity. This is exactly what you do. You the inspection phase helps you play with different compression methods. You can select from a bunch of kernel implementations that I'll talk about, and you can tune the same way you tune in Triton. And eventually you'll have the compressed matrix, the best kernel code, and the best configuration for the given weight matrix. So sparsity is all about specialization. And here you can actually specialize. Your inspector tunes over many options to create a specialized code for that given weight matrix. So the first phase of inspection is you take the matrix and you tile it, and then you compress it. One pre-built feature in Stoic right now is we compress it this way. We take all the dense tiles, put them together, have a CSR running around it, and the same for the sparse tiles. So that's and the compression will change as you change your configurations and your kernel code. And this happens through the inspector. Now, the more exciting part is the kernel code. So the kernel code is very similar to the way you would work in Triton. So how do we work in Triton? You just talk about tiles. You don't care about your memory hierarchy. You don't care about anything. It's up to the compiler to lower that. You just talk about loops around tiles, and you have to be aware that you're running this on a GPU, for example. So you would have each of your GPU programs take care of, for example, here, one output tile, and iterate over relevant input tiles. So that's for dense. For sparse, all you have to do is you have to talk about your sparse tiles. And that's pretty much it. So now you can come up with specialized kernel code for the sparsity. So maybe you want to have each stream of the GPU. Oh, go ahead. I did a question.
I mean, you said compressed sparse rows in 2 slides ago.
Yeah.
I wonder if it's true, because it would be pretty crazy to use CSR for a 4-bit quantized data where the index overhead would be 4 times more than the values that are stored.
These are not quantized, but if you get to quantize, you have to figure out some other way to compress and talk about it.
The CSR is just for the location of the tiles.
Yeah, and the CSR is like a blocked version CSR. Oh yeah, I missed that one.
It's for the...
Yeah, of course. I mean, everything else, I mean, the 2-4s are compressed already. There's nothing special for that. So then, so for example, maybe you want some of your, like, part of your GPU streams or CTAs to take care of dense and then sparse, and then you have a separate buffer to reduce them. Actually, it's very funny. When you talk to somebody that writes fast kernels at NVIDIA, they have no clue whether this is faster or the other one. It's very interesting that when it comes to sparsity or something different that they haven't worked on, they will know. And there's it's really kind of weird barrier of entry to go program for this, because they can't just do this. They have to go write the entire CUDA stack to kind of implement such an implementation. And you can do more interesting stuff. For example, because these are 2-4 sparse tiles, maybe you want smaller tiles for the sparse ones and bigger tiles for the dense ones. So you can create a dense view and a sparse view. And you can even have a very kind of specialized runtime to schedule these. And these are kind of example kernel codes we have in Stoic. And the maybe key point here is it's extensible. You can go in and you can come up with new ways of running your sparse tiles. Now, this is what the programmer that cares about schedules and performance sees. If you want to go deeper, you can go and contribute to the Stoic lowering. So what we've intentionally done is that this is the Triton program that one would write. And the blue is pointing to the sparse data, and the orange is pointing to the dense data. Everything else in Triton stays the same. We do not have a sparse dot. We don't talk about metadata, nothing. You just point the Triton compiler to the sparse data. It's through the lowering passes. And this is kind of, if you do anything besides that, nobody's going to use the tool. People are very, very kind of not so happy with diving into things and working with pointers and thinking about sparsity. So what instead we do is we introduce passes in Triton. So the first lowering pass in Triton realizes that this is a pointer to sparse metadata. It tags it with an encoding. This is an NVIDIA 2-4 sparse matrix. The next stage, it understands that, OK, there's a metadata associated with this sparse tensor. So it creates and separates that metadata. In the next lowering, it introduces a sparse dot. And I'm not going to show you the rest of the lowering, but we go all the way to PTEX to be able to really get the best performance we can get out of the 2-4 execution. So if we pop up now in the inspector, you can go and introduce kernel codes, or you can use the current built-in kernel codes. And then similar to Triton, there's an auto-tuning happening. It takes a schedule, it takes a configuration, and it runs it, and every time it has to compress the code, and it gets the results. The auto-tuning process gets to find the fastest code. This is how Triton works. People are OK with this. So the configuration, for example, here, if you wanted your tile sizes to be variable across sparse and dense, then you can introduce, this goes back to the question on tiling. Stoic itself will go and search in a bigger tiling space. It's just that during post-training, post-training is expensive. We don't want the model builder to go and train for like a 64 by 64 model. Instead, we give them like the best that we can then further down the road kind of tile and figure out what's the best tiling configuration. And then it kind of compresses it, runs it, and so on. The fastest implementation goes to the execution, which I'll talk about. Now, if there was somebody that's done build model recipes, they would walk out by now, because everything I showed was too much code. And what they care about is, in my PyTorch program, writing my modules, give me 3-4 lines of code to call your tool, and that's it. I don't want to deal with anything else. So what we've done is we've kind of, as a programmer in PyTorch, you just create an inspector object. You pass your weight matrix. It's going to spit out the best configuration. And then instead of calling the torch matmul, you just call our matmul. And Triton's already compiled with PyTorch, so you can just use it. So it's very kind of easy to use and integratable. So going back to Pash plus Stoic, actually this was the only way I could convince my students working on Pash to use Stoic. There was no other way. And so if I mean, I've already showed part of this, but this kind of story really tells, this tells a story of there's a knob here, and you can decide how much accuracy you're willing to give for the amount of sparsity you want to introduce. And for now, these are the speedups we get. They might not sound very big, but they're actually very important and big for inference. So on the A100s, you can get like around 16% improvement if you're willing to give more of your accuracy away, or you care about compression more. And this differs right now. We're adding Hopper and Blackwell integration. One of the reasons that one of the things we see that this can get significantly better is that we're stuck with what the Triton programming model provides in its DSL for control. For example, you cannot control shared memory in Triton DSL. So one of the kind of bigger projects going on is, what is the better compiler IR, or IR in general, that you can express those and it can correctly lower the code. So as those evolve, this becomes more powerful, and you can even do more specialized sparse things. That's it. Yeah, I mean, that was the kind of, I already talked about this slide. We're working on this as things progress. I'll answer questions. Thanks.
Questions?
So if I'm understanding your sort of stoic structures, you have a bunch of dense tiles, and you're adding it to, I wasn't very clear, was this completely unstructured or 2-to-4 structured?
For now, it's just 2-4. So you have 2-to-4, which by itself is somewhat unstructured because you're also fine-tuning over the location of those 2 elements out of 4.
So one can think of this as essentially one member of, I guess, a hybrid family of sparse matrices.
Exactly,
right?
yes.
Block sparse plus 2-to-4 sparse.
Yeah. And then if you can lower for CSR, which we can't do now, it's a lot of hard work. NVIDIA GPUs are really, really bad with anything that's unstructured. But if that does happen, or if there's kind of another, kind of maybe a 4, maybe another kind of 1-4, or I don't know, 1-8, or whatever, 2-16 tensor core, you can always add that.
There's been a line of work on taking these weird unstructured-ish looking sparse matrices and trying to turn them into like products of sparse matrices. Or
right.
I'm curious if you've thought of hybridizing those families with, you know.
You mean the families that reorder these matrices in some form to extract some structure from it, or taking them and then decomposing them into maybe a sort of composable, partly structured matrices?
Yep. adding some of these partly structured matrices to like block sparse matrices or something like that?
I think that's possible. The thing is, we have not been successful. I haven't seen a lot of successful work, especially for AI sparse workloads, that you can really extract that kind of structure. The cool thing is you have to go back to the model and post-train that for the structure you wanted. That's where this co-design is really, in my opinion, way more approachable and kind of impactful versus we figure out how to play with our sparsities and create extract structure, and then we hope that the model builder understands this and goes on. Yeah, but anyway, I think possibly this can be extended.
In general, maybe a general high-level question is, does sparsity structure, the sparsity structure you decide to post-train your model onto significantly affect performance?
Of course.
Model, accuracy, not.
Yes, yeah, it does. And that is why the 2-4 sparsities are at 47%. Well, with this tuning now, we get closer to the 54%.
So weight sparsity, this is all model sparsity, right? Weights in the models. And it kind of has a ceiling. What about the application of this tile-based thing to other forms of sparsity, like attention sparsity, like Aparna talked about?
You mean like the input sparsity, something that's dynamic?
No, more like
yeah,
attention.
Yeah, okay. I think so. Even there, I think you can try this and see if that's what you pointed. If you can apply these to kind of attention sparsity and see if it works. We haven't tried. We've tried it in these models and these LLMs, but. Okay.
So how did you tune the sparsity knob, like the 25%, 35%? Is that all trial and error?
No. So in the kind of the last function that you have there, you set here. In the formulation, you set the end goal sparsity that you want. Like you want it to be X% sparse, and then during the post-training, you try to kind of get close to it. So you set that a priori. Cool. Thank you.
Thank you very much.
Oh, microphone.
You still have the microphone?